let's consider a silicon crystal. And if we add the element from the group 3 element, which is actually the boron, into that silicon crystal, the p-type semiconductor will be formed. If we add the 5 group element into the silicon crystal, the n-type material will be formed. Okay, now here in this lecture, what is the diode? Diode is actually the PN junction two-terminal device. This diode have two terminals. You may see such like a shape in the circuit of if you open the charger, okay, inside that the circuit of the charger, such a shape will be present. Okay, that is called the diode. So in this diode is actually the PN junction device. P mean p-type semiconductor, N mean n-type semiconductor. If we take the p-type semiconductor, bring near to the n-type semiconductor, make the contact between them, exert pressure from both sides. Under high pressure, their two materials will become a single material, and that single material is called the diode. Okay, so diode is that simple. This is the symbol for the diode. This side here, this is arrow like side of this symbol will represent P. This vertical uh, line represent N. Okay, so this is the overall symbol for the diode. This side represent the P, this side represent the N. Okay, in p-type semiconductor we have holes as a majority charge carrier. In n-type semiconductor we have the electrons as a majority charge carrier. Now, if we bring these two materials together and exert the horizontal force on these two materials and bring them near to each other and under higher pressure, the junction will be formed between these two materials. And that junction is called the PN junction, and that is represented by this. So what is happening inside this junction and what is the physics involved here? That is so simple. That is so simple, and because here we have the electrons in majority charge carrier in the n-type material, that electrons jump here to the p-type material under higher pressure, and in the p-type we have the holes. That electrons from the n-type will recombine with this holes in the p-type. Okay, and overall that electron has recombined. Okay, so from here this electron will jump and will recombine with this hole. In this side we have the positive charges has remained, and in this side we have the negative charges has remained in this junction. Okay, why this positive? This positive is actually representing the their ability to have electrons, mean that their ability to accept electron. Okay, so it have the electrons. Due to that, this p-type material have no overall charge. It is neutral. Okay, now that electron has recombined. Now as a whole, in n-type material we have these charges appear. Okay, these charges and the atoms appear, which actually represent their acceptance. It is actually the representation of their acceptor core. Okay, and here this is actually the donor. Okay, it has the ability to accept the whole. It have the ability to accept the electron. So therefore the positive charges appear, and this end in this side toward the junction in the n-type semiconductor in the n-type material. Okay, and in the p-type semiconductor material we had these negative charges appear. Okay, so at this junction, electrons from the n-type fill the vacancies in the p-type region. Thus, the negative charges and the negative and the positive ions are formed. Okay. Now, this junction is called the PN junction. Okay. These ions, which is actually these positive ion, these are the negative ions. Okay, there will be the electric field present between these positive and negative ion, and here towards the towards the n type material in the junction, the positive charges are present, and we know that the electric field originated from the positive charge, and that is terminating in the negative charge. So therefore the electric field is from the n type semiconductor material to the p-type semiconductor material. Okay, so these ions form the electric field from the n-type semiconductor to the p-type region. Okay, semiconductor material region. Okay, so in this case, these ions, these negative charges and these positive charges are immobile. Okay, they do not move, just like the holes and the free electrons in these region. They do not move. These are actually dead atoms. Okay, and they do not move. So therefore, these are immobile ions. Okay, and in this region we do not have the free electrons or the holes, just like in this region. In this region we have the large number of the free electrons and less number of the holes. Okay, here we have large number of the holes and less number of the electrons, and these are responsible for the conduction. Here we don't have that ions. We don't have that free electrons and that holes. So therefore this PN junction region is deprived of that holes and electrons. So therefore this region is called the depletion region. Okay, the junction region is free of the electrons and holes, so therefore it is called the depletion region. Okay, depletion region. And here must be the potential, which is actually that potential barrier, because here we have the positive charges, this is the negative charges, and there's some potential difference, and that is called the potential barrier. That potential barrier is responsible to stop the motion of the free electron from this region towards this region. So let's take the further close look of this. Here we have these electrons. If they try to move towards these holes, okay, in order to recombine with them, if these electrons start motion, okay, here we have these negative charges. These negative charges repel that free electrons, and therefore these electrons do not cross this PN junction region. Okay, so therefore this region is called the potential barrier. This is actually barrier for this electron. These positive charges is actually barrier for these holes in the p-type material. So therefore this region is act as a potential barrier. Okay, so the width of this depletion region depend upon the carrier concentration. If we have this, if the impurity of this n-type semiconductor is more, or p-type semiconductor impurity is more, then this depletion layer will be less and the electric field will be high, strong enough. The potential barrier will be more. These electrons will required enough energy to jump from this region to this region. Okay, let's take another close look and in more detail. This potential barrier in the crystal, in the silicon crystal, if we have the silicon crystal on top of it, if if we have the silicon crystal, in this side of the silicon crystal we add the boron atom, which is belong to group 3, the p-type region will be formed. In this side, if we add the elements from the group 5, the n-type region material will be formed, and here we'll have that that PN junction. Okay, so what I'm going to say here is that if we have the silicon elements in this case, then this potential barrier will be up to 0.7 electron volt. Okay, so this potential barrier which is formed due to these ions will be 0.7 electron volt. In other words, we can say that if we provide the external if we provide external voltage to this material, to this PN junction diode, the if that external source have the potential, have the voltage below the 0.7 volt, then here the potential barrier will be present, and these electron will be not recombined and jump to this p-type region. But if that external voltage is increased, it is reached to 0.7 electron volt or exceed that 0.7 electron volt, then this potential barrier will be gone. Okay, this will be vanish, and all these electrons will start motion towards this p-type region, and they will be recombined here, and this diode will behave as a conductor. Okay, it will allow the charges, and the charges will be flow. Okay, so that was the detailed explanation about the combination of that, what will happen if we combine this n-type material and this p-type material under high pressure. Okay, under no biasing. So still we do not provide the external battery to this material, only we exert the pressure on both sides and we combine that n and p-type materials. Now, if we provide the external source, the external battery, then what will happen to this material? So on the basis of the biasing is actually the providing of external source. We divide this diode have the two types of the biasing. One is the forward bias, the other one is the reverse bias. Okay, so let's start the forward bias. Forward biasing. In forward biasing mode, we have that same semiconductor, and the physics behind that we have discussed in this lecture in more detail. So if we provide the negative terminal of the battery to the n-type material and the positive terminal of the battery to the p-type region of the diode. Now I will call this material as a diode because that is a combination of the n and p-type material. So if we combine this negative with this n-type material, so in this n-type material we have the electrons, and this negative terminal as a cathode will repel that electron towards this region, towards this PN junction. Okay, and on this side we have that positive charge, positive plate as an anode, and that will repel these all holes towards this PN junction region. Okay, so what will happen in this case? This electron will be full towards this PN junction, and here the hole is moving towards this PN junction region, and if this as I have discussed, is if this battery have the voltage below the 0.7 volt, okay, then these electron will try to recombine with these holes, but due to this potential barrier, they do not do so. Okay, they will do not recombine with this hole due to this potential barrier. But if this battery provide the potential, if the potential of this battery is equal to 0.7 electron volt, 0.7 electron volt, then that whole then this potential barrier will be vanish. These whole electrons, these all electrons will be combined with these holes, and the current will be start. Okay, and that is this scenario. These all electrons will be start motion towards these holes and recombine with that hole, and the circuit will be complete. And this in this setup is called the forward biasing. The current will be start in this circuit. That current is called the forward current. Okay, so in this case, these electron will be combined in this hole, and this hole will be moved in this direction. The electron will be moved in that direction, in this direction, which is just opposite to the motion of the holes, and the circuit will be complete. Okay, so this is the physics behind the forward biasing. Now the last part of this lecture is that reverse biasing. So in reverse biasing, we have this positive. If we connect this positive terminal to the N-type region, this negative terminal to the P-type semiconductor material, then what will happen in this case? So this positive charges will attract these negative charges, which is in majority is a majority charge carry. Here is the N-type material. Okay, they will attract that negative charges towards itself, due to which this depletion region will be higher. Okay, these electrons has pushed towards this side. Similarly, these holes are attracted towards this side, because in this side we have this negative charge. Okay, this negative plate of the battery. So due to this negative terminal, these charges will be attracted towards this side. Okay, due to that, this potential barrier will be more, the electric field will be more, due to which this PN junction will be wide. Okay, because all charge carrier has attracted by this battery, and due to which this depletion region will be more. This is that depletion region has increased due to this external battery. Okay, this positive charges attract the negative charges of this N-type material. This negative charges attract the holes, which is majority charge carrier here in this P-type region towards itself, due to which this depletion region will be more, and the current will not start. These electrons will not recombine with these holes, and the current, there will be no current in this scenario in the reverse bias, and so there is no current. So therefore this arrangement setup of this diode is called the reverse biasing. Okay, so this is called the reverse biasing. If we connect the positive terminal with the N-type region and the negative terminal with the P-type region, the P-type materials, the semiconductor material, then the depletion region will be more, and the current will be not there will be no current in this case. Okay, so this was the detailed overview about the what we can say about the diode. Okay, so we had discussed that in more detail. So let's take a quick recap of that within 1 minute. Okay, so this is actually the diode which is formed by the external pressure and the p-type and n-type material, and we bring that, and in that contact region the majority charge carrier recombine, and such type of the region is formed having positive charges on one side, negative charges on the other side. The electric field will be produced from this positive region towards this negative region. Okay, and this region is called the PN junction region, and here we do not have the free electrons and holes, therefore it is called the depletion region. These ions are immobile ions. If we provide the external battery to this, if we connect the negative terminal to the n-type material, the positive terminal to the p-type material, this negative terminal will attract will repel these electrons. This positive terminal will repel all these holes, and a time will reach all these electrons will combine with these holes, and the current will stop motion, and this sort of arrangement is called the forward biasing. And in the reverse bias, if we connect the positive terminal with the n type, it will attract that negative charges towards itself. If we connect the negative towards the p type, that will attract that holds towards itself, and due to which this depletion region will be more and no current will be pass in this case in the semiconductor. So this behavior of the diode, this behavior of the due to this behavior of the diode will be used for the rectification purpose, and we will discuss that in the next video. And that's it guys. Thanks for watching.